Okay.
Sorry, let's let Professor Baker get us going.
Well, first let me say that I can now return the favor and say it's a very hard act to follow Tom. I didn't realize it would take that long for me to follow Tom either, but that's another question. But I'm delighted with what he's presented, and it's really an honor to be a colleague of his at the University of Colorado. I'm in the same department as Tom, in the Department of Astrophysical and Planetary Sciences. I'm also at the Laboratory for Atmospheric and Space Physics here in Boulder. And my work has revolved around studying the Earth and the planets, primarily the magnetospheres, and in particular studying energetic particle phenomena in these various environments. And my work has also dealt a great deal with the studying of the coupling of energy from the solar wind and the sun into the Earth's magnetosphere and other magnetospheres. And one aspect of that I'll talk about a little bit is space weather. This is the outline for my talk today. I'd like to give a little bit of introductory stuff, talk about some of the solar and solar wind drivers, and many of the things, in fact, coming late in the summer school sequence here, you probably have heard about almost all the things that I'm going to talk about today. So I hope that some of this will bear some repeating. I'll talk about the Earth system response in various ways, maybe giving a little more emphasis to the space weather kind of things and the radiation belt kind of things. And I believe you've heard even today about some of the other planets, so I won't dwell on that, but maybe some of the things you haven't heard so much about, like Mercury, for example. Let me say that I feel I have to quote here Tom Mancuso, who said, stealing from one person is called plagiarism. This is very important for our students to learn here. Stealing from many people is called scholarship. And this will be a very scholarly talk. So I've stolen extensively from many colleagues and friends around the world. Going to this picture, this is one kind of nice artistic diagram that goes to the point that the kind of science that we study in looking at the connections between the sun, solar forcing, and the Earth's response is absolutely intriguing, despite Tom's ladder. I think it's a fascinating and quite fascinating thing to study our local astrophysical environment. But it also does bear quite directly on things that affect humans in a very direct and personal and daily way. Looking at the sun, looking at the effluence from the sun, looking at their consequences in the Earth's vicinity is quite interesting from the scientific standpoint, but it also has implications for the power grid, for operation of satellites, even possibly some connections to climate change. This is a diagram that you've seen many different kind of diagrams of sunspot number versus time. This is from David Hathaway at Marshall Space Flight Center. But it shows cycles going back to the 1980s. And this looks like sort of a going out of business curve for the sun. The large activity back in the 1950s and 60s and into the 70s and 80s. And then this progressive decrease in the peaks of sunspot activity in relatively recent times. And as Tom talked about, and probably other speakers have talked about, it's been puzzling as to this very deep minimum that the sun went through and the very anemic kind of maximum now. What will happen next? And every time solar modelers tell us with confidence that they know what's going to happen next, then the sun does something different. So the next activity cycle, the next minimum will either be a very deep minimum or not so deep. The next maximum will be either a smaller one or a larger one than this, probably not exactly the same. And that's what passes for space weather predictions in our field. How do we study this? I guess that's one of the themes here at this in this latter part of the school is talking about a lot of the tools that we use. We use, of course, ground-based facilities. We use a wide variety of satellites, spacecraft that are operating. And this is one illustration. I know earlier in the week you've heard other people's renditions of this Heliophysics system observatory, but it really is a remarkable time for studying the connected Sun-Earth system because we do have all these assets in space, all of these that are looking either at the Sun or looking at the response in various points throughout the Earth system, or even extending out to the very edge of the solar system with the Voyagers now. And so you as students who are getting into this business in a really serious way, should realize that we have an amazing array of tools. I'm going to tell you about only a small number of them, but I think, again, that during the course of this school, you've learned a lot about a lot of different ways to study this connected Sun-Earth or Sun-Planetary system. This is a diagram that was used in Tom's talk and is used by many people, the Yoko soft X-ray images over the course of the 11-year cycle, going from active to solar minimum kind of conditions, then back to active, approximately 11-year cycle. This is the dominant kind of season, the dominant kind of variability that affects the Earth and the planets. But there are many others that we'll touch on some of those. Now, I know Tom was kind of disparaging of the importance of, at least from an energy and mass standpoint, of coronal mass ejections, but this is a diagram that you may have seen earlier in the school. I like very much, that illustrates an area of activity on the Sun, some loss of stability, the release of the coronal mass ejection, the billion tons of material. Prototypically, the thing we are concerned about, say from a space weather standpoint, is how this can interact if the interconnection takes place, loading of energy into the magnetospheric system and then the rapid dissipation of that, and ultimately the leading of that to enhancements in the near-Earth region. This is the kind of event that's fascinating from a scientific standpoint, and it's also probably the prototypical concern one has for space weather, because that kind of imparting of energy and the intense flowing of currents in the auroral and subaraural and even mid-latitude regions can be one of the principal causes of disruptions to human technologies like the power grid. Now, there have been many tools, and again, probably during the course of the school here, you've heard about many of these tools. I think one of the truly transformative ones was and has been the Solar Heliospheric Observatory, SOHO, that has provided a sentinel of looking at the Sun, giving us increased warnings, increased alerts of when the Sun is active and when large blasts of material coming from the Sun toward the Earth. And so these kind of data have been fascinating from a scientific standpoint and have given the kind of eyes on the Sun that have really been needed in order to give effective space weather forecasting as well. Now, very recently, just a couple of months ago, this image was taken with SOHO at 284 angstroms. It shows something about the Sun. Again, my apologies for not being at all the lectures here, but I just ask you to look at the northern part of our Sun. And it's sort of a vast barren wasteland here comparatively. The southern part is quite different in effect. It's very active in the southern half of the Sun. Large coronal hole here, which, as you've heard about in the lectures, giving rise to high-speed solar wind flow. So the combination of high solar wind speed, high streams that are impacting the Earth, and active regions that are giving rise to coronal mass ejections mean that we're really being subjected these days, and these specific days, by two different suns. The very quiet Sun associated with the northern part of the system, and the southern Sun, which is giving us the kind of activity that is affecting our technologies right now. Going back to an animation of earlier times with SOHO, but some of the points that have been made about coronal mass ejections, why we are concerned about them as a driver of the system, is really shown here, remarked upon. These occur with greater frequency near the peak of the 11-year cycle. They can propel large amounts of material toward the Earth. If they impact the Earth, they can really drive strong activity, and triggering this kind of storm activity on the Earth is, again, one of the things that we find most interesting and probably most unsettling about the sun's effect on the Earth system. If we go back to near the peak of the last solar activity cycle, not the one we're in, but back in 2003, there was a very strong active region on the sun that caused huge outbursts, not once, but multiple times. These were called the Halloween storms. They occurred at the end of October 2003. And what you see played out in this sequence is the kind of all of space weather just played out before your eyes. This will start with a flare, an active flare region. This, in turn, led to a coronal mass ejection being released here. The snow that you see in the picture is very energetic solar particles that are blinding the detectors in space. The blue that we'll cycle through again here in a minute, the red and blue, then shows coronagraph pictures that show the halo kind of coronagraph coming directly toward the Earth. And this is a particularly nice picture of that. So very rapidly flowing plasma coming directly toward the Earth. And this caused a whole host of effects in the Earth system. And the kind of blinding of the detectors in particular suggests something that if you were in space, if your eyes or your brain were in space, you'd be subjected to those same very high energy particles penetrating. And astronauts have a considerable concern about that. So that's a picture of the strong driving from the sunward side. What about the earthward end? Well, we have many tools. I think one that you probably didn't hear much about in the earlier lectures in the school this summer, but one that I think has played a very important role and one of my favorites because I was an investigator and the project scientist on this for a number of years. It's called the Solar Anomalous and Magnetospheric Particle Explorer, SAMPEX. And this mission was really in low Earth orbit. It was geared toward, as the name might imply, studying solar and solar particles, anomalous cosmic rays, and the magnetospheric response. And so we were able to look at solar energetic particles impacting down into the Earth atmosphere, into the lower part of the Earth's magnetosphere. We were able to study the radiation belts themselves by techniques I'll show you in a second. We were even able to look at the effects of these particles down into the Earth's atmosphere and understand their effect on such things as ozone and minor constituents in the atmosphere. Now, using a satellite that is flying around in very low Earth orbit, you might wonder how much can it really say about this vast expanse of radiation outside the Earth's volume. And so one way to think about that, and you probably have seen variants of this, but this is a very large electron moving around a magnetic field. And it's undergoing first its gyro motion. Now it's bouncing back and forth between the mirror points, as they're called. I think John Foster introduced you to this concept. We have sort of poor lighting here for this here, but the little electron is now undergoing both its bounce and gyro motion, and it's also going to be drifting around in the Earth. If you think of not just one particle executing this kind of motion, but you have trillions of particles executing this kind of motion, then they paint this kind of radiation belt structure. And so that's really the way that a mission like SAMPEX, measuring at the foot of the magnetic field lines, is still able to kind of bookkeep all of the electrons, all the particles, or a significant number of them that are moving around in this radiation volume around the Earth. And of course, this, as was introduced by Dr. Kessel and also Dr. Foster, these are the Van Allen radiation belts. And SAMPEX really did a marvelous job over a period of almost exactly 20 years of looking at the radiation belts. This diagram shows you the inner Van Allen zone, the outer Van Allen zone, the region of paucity of particles in between, the slot region as it's called. And if you bookkeep the particles by looking at where they are on field lines that cross the magnetic equator here and measure that in Earth radii, that's called the L parameter. And here's then a plotting of the inner zone, the very close to the Earth, out around 4 Earth radii is the heart of the outer Van Allen belt. Out at 6.5 Earth radii is where geostationary orbit satellites operate, the GOES satellites and so forth. So this is a great picture over a period of more than a solar cycle of the variation of the radiation about, and in this case, multi-MeV electrons. And this is like 5 orders of magnitude in the color scale. So there's a high degree of variability for the radiation around the Earth. Dr. Kessel talked about the discovery of the Van Allen belts. I think one of the most interesting parts of the story she didn't tell. The Sputnik was launched in October of 1957, had a radio beacon, and that was about all. But about a month later, the Soviet Union launched a second Sputnik, Sputnik 2, that had the dog Laika on board, but it also had a very complete package of space radiation detectors from, and it was Sergei Vernov from Moscow State University who had the instruments on board. The Sputnik 2 had an apogee that was over Australia, not over the Soviet Union, and so the data were encrypted, and the Australians recorded the data and asked the Soviet Union for the code in order to interpret the data. The Soviets refused to give the code. The Soviets demanded the data from the Australians refused, and so the Vernov belts faded into oblivion, and it fell then to Van Allen and co-workers to discover the radiation belts around the Earth. So I know that many of you are going to be working in the international arena. Let me urge you to be cooperative, share your data, and share the code. And if you do that, I think you'll be better off, and science will be better served. At any rate, the Van Allen belts, not the Vernov belts, are displayed here. And one interesting thing, I showed you the October 2003 period. At the end of October, that large coronal mass ejection sequence of coronal mass ejections impacted the Earth, completely distorted the radiation around the Earth, led to a huge enhancement of the electrons very close to the Earth, completely changed the entire structure of the Van Allen belts for weeks, in fact, for years thereafter. And so the normal kind of outer radiation belt, the outer Van Allen belt, looks like this. It's related to where the coldest plasmas are, the plasmasphere that you've learned a lot about, I know. But when you sort of eradicate the plasmasphere and allow it to reform much closer to the Earth, as has happened during the Halloween storms, then the Van Allen belts also change. And so as the headline here really says, it's often the very coldest particles in the system through the waves that they support that dictate how the very highest energy particles really behave. And that's one of the fascinating things that we study by having these multiple spacecraft available to us. Another mission that I know you've heard some about is the 5 spacecraft THEMIS mission. This was led by the University of California, Berkeley. And we were pleased at my lab to be pretty actively involved in this as well. And to use then, again, multiple spacecraft arrayed in a carefully thought out way down through the system has really given us a much more complete global picture of how the magnetosphere varies and how it changes with time. In fact, I wanted to, I don't know if you've seen this animation before, but we developed this to convey the idea of the fact that this system, which often is portrayed in diagrams and textbooks, of course, as very smooth and laminar, is anything but. The changes that are occurring on essentially all time scales. Here we have the magnetic field portrayed. We have the outer boundary of the system. As THEMIS and other spacecraft have illustrated, this is an undulating, constantly changing, and constantly exhibiting dynamics. We have the bow shock out in front that you've undoubtedly learned quite a bit about, slowing and diverting the flow of the solar wind around the object. The magnetopause surface itself, which can be either a gateway or a barrier to entrance of solar plasma. Under the right circumstances, then, we have the plasma sphere and the ring current and the radiation belts all commingled in this inner part of the system, responding in very substantive but very different ways to the external forcing. The most interesting forcing to us is often the enhanced flow of solar wind, either through high-speed streams or coronal mass ejections. Energy is then stored in the night side in the plasma sheet region, and that energy storage can play a huge role. And then the Dungy cycle that you've undoubtedly heard a great deal about, where magnetic field lines in your planetary medium interconnecting with the Earth's magnetic field, conveying this energy into the tail and enhancing the whole interaction quite substantially. And then the return of that flow of energy through magnetospheric substorms and storms down into the auroral regions, enhancing the auroral activity, of course, but also in the process enhancing all of these other populations of particles. Ultimately, we can see a lot of this on the TV screen above our heads, the auroral enhancements. And those auroral enhancements, again, have many technological implications and consequences quite often. So that sequence, that's a very important part of the seasonal interaction with the sun. And we're now studying with the Van Allen probes, or radiation belt storm probes, and a very recently launched spacecraft mission called Magnetospheric Multiscale, 4 spacecraft flying in close constellation that are going to tell us much more about this reconnection process. So again, I would just drive home the point to you that although we often, because of our interests or proclivities, study one aspect or another of this, this is really a tightly coupled system. The sun is tightly coupled to the Earth and the planets. But within the Earth system, for example, we have this coupling between the plasma sheet, the ring current, the plasmasphere, and tools that we've had in the past, such as the IMAGE spacecraft, the imaging of the magnetopause to the Aurora geospace exploration mission. These have been spectacular successes that have allowed us to step back and look down on the system to look at the Aurora as these the global kind of imaging systems that were on board IMAGE, which we need again, by the way. Also, the ability to explore through the process of energetic neutral atom imaging to be able to see the ring current and its development. And this set of diagrams from Jerry Goldstein also illustrating the idea. There's a little admixture of helium plus, singly charged helium in the plasmasphere along with the other ions, the protons and so on. And by using the extreme ultraviolet from the sun and looking at its resonance scattering, we can actually build up pictures, global pictures of the plasmasphere. And I know you've seen these kinds of pictures in other lectures before, but it's quite remarkable that we can step back and see this kind of very tenuous, ghostly kind of cold plasma around the Earth and be able to study its interaction and its role in the radiation belts and so on. Let me go back now to the very high energy particles for a second. This is another version of what I showed you before, the long run of SAMPEX data. And just note that the variation of the radiation belts is really quite highly variable from one season, from one year to the next. But if you look at it in broad terms, again, this is a 5 orders of magnitude color scale here. The highest intensities of electrons that we saw in the outer Van Allen belts in earlier times from SAMPEX were not at sunspot maximum. Here's the sunspot number up here. They were really in the declining phase of the solar activity cycle. And this is really a time when the solar wind is at its highest speed. This is when the coronal holes and the high-speed streams in the interplanetary medium are occurring. So the radiation belts do exhibit an 11-year kind of dependence, but it's not that at the highest sunspot number we see the highest electrons in the radiation belt. No, it's really during the declining phase. We saw that repeated back here on the declining phase of this last approach to solar minimum, and now we're in that sort of same phase again, where we're again seeing quite a strong enhancement of radiation belt particles with the Van Allen probes, and I'll talk a little bit about that. Now, if we look at the data from the SAMPEX mission and really separate it according to not the sun's seasons so much, but the Earth's seasons, we have found some intriguing things that we still don't fully understand. We find that in the spring and fall, that is the kind of around the equinox periods, The radiation belt content, the radiation belt intensities at Earth are about 3 times higher or more than they are around the solstice times of summer and winter. This is a very puzzling phenomenon. It may be related to the same kind of variation in activity of geomagnetic activity that I know you heard about from, say, John Foster, the so-called Russell-McPherson effect. But that's a pretty subtle kind of thing, a few percent kind of variation in many cases for the geomagnetic activity. Here we're seeing a huge, huge difference in the way the radiation belts work in the spring and fall compared to the summer and winter solstice times. And so we've studied this using other methods. This is a paper by McPherson et al. And of course, what you see here with the colored lines in the middle is the kind of average behavior over the course of, in a superposed epoch sense. And the sun knows nothing about the Earth's seasons, really. And the solar wind certainly knows nothing. And so it's a very flat distribution, as you'd expect it to be. Yet, when you look at this, you see that the radiation intensities in the radiation belts show this huge variation. The radiation belts are known to be driven by the high solar wind speeds, but they also exhibit another kind of seasonal dependence that we're still scratching our heads about. Now, the Van Allen probes were launched very successfully in late August of 2012. They were expecting to find 2 Van Allen belts, an inner belt and an outer belt. And we turned on our instruments about 2 days after launch, and we immediately found that there were not 2 belts, but 3 belts, and that's illustrated back here. And so we found that the textbooks, I guess in a sense, had been wrong for 50 years, and that there really was a 3-belt structure on occasion, what we called the storage ring. And we also then found many of the things that John Foster pointed you to, that often those radiation, the radiation around the Earth can disappear almost on a knife edge. It can reappear almost as abruptly. The particles can be hugely intense. They can die out over periods of weeks, months, even the better part of a year. We also found this very puzzling feature that the very high energy particles, in this case multi-MeV electrons, go in only so far toward the Earth, and then they seem unable to go any further. We've termed this the impenetrable barrier to ultra-relativistic electrons in the Earth's radiation belt. And what this really shows is that there is some kind of a barrier almost to high energy particles getting through. They can approach, but never, at least during the lifetime of the Van Allen probes, have not been able to penetrate any more deeply than that. This is work now that we're just submitting to the journal Science, but it really seems that the cause of this barrier has a great deal to do with human effects, not so much natural, but it's really humans have been causing this. And it is because the Earth is surrounded by a bubble of very low frequency waves that come from high energy, high power radio transmitters on Earth. These are used by the US Navy to communicate with submarines. These have been operating since the mid-1950s. These transmitters actually do extend out, their influence extends out precisely to the place where we find this impenetrable barrier. And so the kind of interesting and maybe even shocking thing is that we've never seen the Van Allen belts in their pristine state. They were discovered in 1958. The transmitters have been operating since before that time. And so humans have not only been polluting the Earth and its atmosphere, but have also been polluting the radiation environment around the Earth. And okay, I'm happy to have Nick lead the charge on that one. Now, what about, so this is a little bit about a reminder, a refresher course to you guys on some of the Earth story. What about other planets? Well, I didn't hear Fran's lecture today, but I'm sure it was a marvelous lecture, and probably focused on the outer planets, if I'm any judge of. Okay, here's Mercury. So we've been delighted to have not only this wonderful view of the Earth and its environment and the sun, but also other planets like the Messenger mission at Mercury, which unfortunately has come to a crashing end. It collided with the planet in April of this year, and we are still analyzing the data. But Mercury Messenger was in a large looping orbit around the planet, was injected into this orbit in March of 2011, flying both out in the solar wind and then flying in deep into the system. If this diagram looks pretty familiar to you, it's because we're not too creative, I suppose, and we sort of apply our Earth knowledge to other systems. And in many ways, this is the right thing to do. Mercury, surprisingly, has an intrinsic, strong intrinsic magnetic field, even though it's small and presumably has had a long time for this field to sort of die away. Probably has a large molten core. The planet itself fills a large volume of the space around within the magnetosphere, but we still have this standoff of the solar wind, a magnetopause, a bow shock, all the kind of things we've grown familiar with the Earth, a night-side plasma sheet, and so on. The interesting thing about Mercury is that because of its small size and the lack of a very strong ionosphere, the Dungy cycle, which at Earth is about an hour or so, a couple of hours, is about a minute or two in the Mercury case. So it's like the difference between, let's call Jupiter an elephant, and maybe Earth is more like a horse or something like that. Mercury is more like a mouse. It has a very high metabolism rate, and the system is constantly turning over on very rapid timescales. But with Messenger flying in this kind of orbit, we were able to study the boundary locations and understand that in the context of the solar forcing energetic particle things, which I'll tell you about in a second. Plasma waves, a rich environment of plasma waves there, many changes in the plasma density. The plasmas tend to be dominated inside by heavier ions like sodium. That's an interesting aspect. And then magnetic reconnection occurring very, very rapidly in the Mercury system compared to Earth. Does anybody know what the year, how long a year is at Mercury? How long its year is? Pardon? 3 months. Right, 88 days. And how close does it get to the sun, Mercury as a planet? 0.3 AU. And how far away at its maximum distance? How about 0.47? So it's got a very large eccentricity. And by looking at the magnetic field data, which are these black spikes here from the Messenger magnetometer, after injection in 2011, we then are able to just look at the variation, and we're seeing many, many Mercury years here played out before our eyes. And we're seeing the high degree of variability of the magnetic field strength when we're out furthest away from the sun, a relatively weak field on average, moving in toward the sun closer, seeing stronger field. So in the Mercury case, it is being driven much more strongly by the changes in orbital position than is the case for the Earth. We've also used some of the models that have been used for space weather forecasting, the NLO model, for example, just to try to emulate what the field variations might be. But so Mercury is at its largest extent is subjected to relatively much weaker kind of solar wind strengths. The flow speeds are the same, but the densities are down substantially out at these distances. As you get closer to the sun, it's really quite a strong forcing of the system, and so this is one of the contrasts, you might say, with the Earth system. I mentioned some of the things that we've been finding very recently about Mercury, and this is an examination of the energetic electrons in the, let's say, a couple hundred kilovolt electrons, kiloelectron volt electrons, measured with the sensors that were originally intended to measure the gamma ray environment around Mercury, but using the kind of background electron measurements from that gamma ray sensor, which is being measured at very high cadence, 10 millisecond sampling. we're actually able to look at energetic electron behavior. And here we have a nice case in a paper that's just been submitted to JGR where we're seeing a very rapid enhancement of the electrons by a large factor. We're actually seeing a complex double injection here. And then we're seeing these electrons come back in a very periodic way. So what we're really looking at is that these electrons are injected by substorm processes on the night side of Mercury, drift around the planet, and can drift around multiple times. So whereas Mercury doesn't have a long trapping, the kind of stable Van Allen belts, it does show quasi-trapping of energetic electrons. And we can actually study their occurrence properties and find that very much like the Earth case, these are produced by magnetic reconnection processes on the night side of the planet, relatively close into the planet, and then these drift around and populate the magnetosphere of Mercury for a limited time. So this again is a perhaps not very creative extension of the Earth picture, but that Mercury, which has a highly aligned magnetic pole, but is undoubtedly being forced in the seasonal way, strongly, less strongly over the course of its year, but that there are undoubtedly strong magnetic reconnection processes occurring on the night side. We see plasmoids, we see the strong episodes of magnetic reconnection over and over again in the Mercury case, and that all of this entire cycle is occurring on very short time scales, like a minute or two. Now, another planet that's in quite yes?
Dan, could I just ask a couple of questions about Mercury?
Sure.
I'm terribly out of date, I'm sure. Could you tell me, you said it's remarkably tightly aligned. Is the magnetic axis really very aligned with the rotation axis?
Yes, very closely, less than a degree. Its magnetic field, however, is the dipole is offset quite considerably by about 1/10 of a planetary radius or more. So it's actually offset toward the north, and so this it's not centered precisely on the center of the planet.
But this must violate Couplings' theorem, right? Or maybe you don't have a problem with this.
Well, it's not going to be anti-symmetric.
Yeah, we're seeing the manifestations outside.
So this is a big issue that planetary dynamos are not supposed to be rotationally symmetric.
Right. Right.
And yet we have two examples, Mercury and Saturn,
Mm-hmm.
which seem to be very tight. So we've got to invoke something else to do this. So here at Mercury, if you were to extrapolate down to the core mantle boundary, you might end up with something that's much less symmetric.
Well, absolutely.
Yeah.
And it could be time dependent, you know.
Yeah.
In the past, it wasn't so long.
My second question is, Mercury doesn't have an atmosphere to speak of. So with the Earth, we had lots of
That's why I didn't speak of it.
about the ionosphere being important for the
Yes.
coupling between the planet and the magnetosphere.
Yes.
So no ionosphere, what's the coupling going on? What's happening here?
Yeah, I mean, I think that continues to be a subject of some discussion and debate, but it really seems like if there are large-scale currents, and there must be associated with this kind of structure, that these must be closing either through this very thin exospheric, the very thin exospheric gases, or else it must really be almost closing through the regolith itself. And so I really believe that this remains one of the puzzles about how such an Earth-like system is maintained, and how these kind of substorm processes can be occurring so analogously to Earth, even though we don't have anything like the ionospheric structure that we do for the Earth as a system. So we believe that almost all the direct analogs are there on this much more rapid time scale, but how the ionosphere plays in that is really a good question. Now, another terrestrial planet that's quite important right now these days is, to us at least at LASP, is the Mars system. because we have the MAVEN mission, as I'll mention in a second. But here, for Mars, in contrast to Mercury, which we just argued has a strong intrinsic magnetic field, here for Mars, it's mostly remnant field in just locations, a few locations in the southern part of the planet. The rest of the Martian system is, there's almost direct or very close to direct impact of the solar wind into the atmosphere itself. So if you think about the Earth case, which with this strong magnetic field standing off the solar wind flow, creating this magnetopause boundary to help sort of protect the system from the solar wind flow, there's much more direct and immediate access of the solar wind, and hence forming a more direct ionospheric contact with the solar wind flow. And this has been an intriguing question of, and this is a very complex picture because I guess it's a very complex interaction. We have all the things that affect the Earth, the coronal mass ejection, the solar energetic particles, the UV, the whole shebang. But in the Mars case, these have been probably for millions, billions of years interacting more directly with the atmosphere of Mars itself. As a consequence, much of the water, much of the atmospheric gas has been carried away over time. And so how is this, what is the bulk escape, what's the outflow, how is all of this really change, and especially what can we learn from the present time that might be applied to understand the past evolution of Mars and therefore understand more deeply what's really been going on with the system. So the MAVEN mission was designed for this. Professor Soika was asking me about the kind of relationship between planetary science and terrestrial science in a space physics sense. I think MAVEN is one of the good examples of how you can pursue very good space physics kind of questions, but in a planetary context. And so MAVEN has really, is really looking at the solar wind planetary interactions, the evolution and loss of the atmosphere, trying to interpret from present observations of coronal mass ejections and high-speed stream interactions and so on, interpreting what the water loss might have been over historical times, and then really trying to apply those lessons more broadly. So this is underway now. A new set of findings from MAVEN have just been submitted to Science, and that special issue should be forthcoming in the next few months. I won't dwell too much on the outer planets story other than to say, and as I'm sure Fran talked about, is that the pioneers and the voyagers made marvelous discoveries about the nature of the Jovian magnetosphere, this huge, dominant kind of magnetosphere in the solar system. The powerful Van Allen belts, the equivalent of Van Allen belts in the Jovian case. In the case of Jupiter, we can see quite directly the synchrotron emission from the electrons. So even before any spacecraft approached the planet, it was recognized that there was a strong magnetic field and that there were strong radiation belts, or the equivalent of belts, in the vicinity of the planet. Going back to what I was telling you about the Earth case, it's kind of interesting to think about that if somebody had been sitting on Jupiter or maybe one of the moons of Jupiter with the right radio sensors back in the 1950s, the Earth might have been a strong synchrotron emitter. And then when we turned on our VLF transmitters, those high-energy electrons disappeared close to the Earth, and so the synchrotron emission probably disappeared. And so these are probably pretty intelligent people who are watching this development, but they might have assumed that the civilization of Earth somehow had gone awry or something, and maybe it did.
So really, Dan, are you saying that the Earth's radiation belts have gone down by a huge amount like that? Really has disappeared? Effectively?
Yes, I am saying that. I think that these would be quite low-frequency emissions compared to the Jovian case, but the absence of, we have almost a complete absence of multi-MeV electrons inside of 2.8 Earth radii around the Earth. if it weren't for these transmitters, I'm telling you, I'm arguing to you, that those high-energy electrons would get in much closer to the Earth. They would be in the strong field region. They would be synchrotron emitting. And so, so I believe that, that we have changed our face to the universe in a significant way. I'm sure that Fran probably also talked to you about Saturn and about some of the fascinating ways that the Cassini instruments have been using, the energetic neutral atom imaging to assemble a picture of what the radiation environment is around the planet. I won't dwell on those things other than to say that, that the outer planets, these are probably sort of outmoded pictures I got from Barry Mock, but Jupiter, Saturn, Uranus, Neptune, each have fascinating similarities to one another and to the Earth, but also have fascinating differences. The main things I guess I would say about Jupiter is that it's highly dominated by its rotation. The rotational energy and the rotational effects completely overwhelm the interaction with the solar wind. That's true to some extent in the case of Saturn as well. Saturn also has the additional feature of having the rings, which can be strongly absorbing the energetic particles. The Jovian system has the large moons deeply embedded within the magnetosphere. Those also have been taking quite a bite out of the radiation belts. And so both for the Saturn case and for the Jupiter case, the moons themselves cause quite an effect on the radiation environment. This is a diagram from Tom Hill that makes the point that Earth, while it is very strongly controlled by the external forcing of the solar wind, the Jovian and Saturnian magnetospheres are certainly shaped by the solar wind flow, but their internal dynamics are very strongly controlled by are dominated in many ways by the internal rotational processes. And this, I think, is from Fran and Barry Mock, just talking about one aspect, which is, I mentioned to you about Mercury, the injection of particles due to this kind of Dungy cycle. Mercury, yes, we're seeing that quite prominently. Earth, of course, yes. There are episodes of injection seen in the Jupiter and Saturn case. Uranus, apparently, yes, and nothing observed so far. And it may be a while before we observe anything further with Neptune, because these things were done with the Voyagers. And I'm not sure when next we will have something going out to the Neptunian world. So finally, let me just sort of wrap up by talking about the largest magnetosphere that we have direct access to of all, and that is our solar system itself. The IBEX mission, the Boundary Explorer, Interstellar Boundary Explorer, was launched back in 2008. And one of its striking observations as it looked out from its vantage point near the Earth out to the edge of the solar system was to see this intense ribbon of neutral atoms. Again, it's using the neutral atom imaging technique. And what it found was over time and in many different energy ranges and so on, that it was seeing a band of high intensity radiation coming from this certain location on the edge of the system. And this has been interpreted. There are probably as many models as there are photons that have been detected, or neutral atoms that have been detected. But I think the general view is that this ribbon is indicative of the kind of interaction of the interstellar flowing gas with our magnetospheric, our solar system magnetosphere, if you will. And this goes back to something that Tom Ayres talked about in his talk, that with Hubble and remote sensing systems, we can look out at other stars and see these kind of walls, the kind of bow shocks and boundaries of other stellar systems. And so very probably, if we were standing 4.5 light years away and looking back at our solar system, we might be able to see something analogous to this as well. So we have the sun in here, the Earth, and all the planets close in. Now the Voyagers have been out flying through the termination shock, headed out toward the heliopause. and eventually may very well be able to explore getting directly out into the unperturbed interstellar medium. But this, in many ways, is, as I say, dominated by the magnetic field emanating from the sun, the flow emanating from the sun, interacting with the external interstellar medium. So let me just conclude my, my lecture here by just reminding that we have the wonderful Solar Dynamics Observatory, we have the IRIS and other missions that are looking at the sun in this spectacular way, and we have now this remarkable constellation of spacecraft that are operating around the Earth. The Van Allen probes have joined, the MMS spacecraft have now joined this. We have the operational spacecraft, the GOES and other satellites that are also operating in this vicinity, and many low-altitude spacecraft. The cluster mission continues to operate in pretty good form. So we have the most amazing set of spacecraft that are sampling everything from near the Earth out to the very fringes of our magnetosphere. And together, these are giving us the kind of picture of what's going on, why it's happening, and when. And now even the Artemis ones are in orbit around the Earth, so around the Moon, rather, extending to a great distance. So this combination of having the solar forcing and the magnetospheric response well documented, I think, is truly a golden age for understanding the coupling between the sun and the Earth and the planets. So this is some of the summary points that I'd make for you, that I think the sun and its variable outputs are certainly the main drivers of changes in the Earth's space environment. The dominant one, as I've talked about, is the 11-year solar activity cycle. It has profound effects on the Magnetosphere-Ionosphere system. The tilted offset dipole of the Earth, that leads to more Earth seasonal kind of effects in the geomagnetic and radiation belt environment. And comparative studies between these various systems I've talked about here today, I think, are giving us amazing new insights into the broader astrophysical questions that Tom Ayers was talking about, and really help us to understand quite deeply the nature of the plasma physical coupling that's going on. So thank you. I'd be happy to answer any questions.